Okay, so this is Unit 7, PowerPoint 1, and Unit 7 is all about waves. So we're going to learn about the different types of waves and what exactly a wave is, and the different shapes of waves and how we understand them. So I'm just going to go ahead and hide myself here so that we can see the lecture. So we're going to start off with just talking about what exactly is a wave. And when people think of wave, they have a lot of different answers. Some people might say like you could do like a wave in a stadium or like a crowd, where you just have like a whole bunch of people standing up when it's their time to stand up, and it just goes around the stadium. Other people might say that a wave could be something like a wave in the ocean or a wave in the lake, where it's like the physical movement of the water, or the water itself is the wave. Well, we know in science that a wave is actually a disturbance that carries energy through space from one place to another. Notice I highlighted the word energy, and that's all a wave is. It's the movement of that energy. It does not carry physical matter. So, if you think about it, like if we go back to the example of like a wave in a crowd, for instance, if you're thinking about like a wave in a stadium, you might stand up and down in your seat to participate in that wave, but you physically are not moving around the stadium. You're still staying within your seat. So the energy is being moved throughout that wave, but the individual particles of matter, they are not going anywhere. They're just standing still. And if this doesn't make much sense, I'll show you a couple of diagrams here in a little bit, or a couple of animations that will make more sense in terms of how the particles themselves don't really go anywhere. It's just that there's energy flowing through them. All right. And a wave is always caused by some type of vibrating source, or a source that causes them to uh, start to vibrate or move in a certain direction. For instance, the most common type of wave that we probably interact with is a sound wave or a light wave. And for like a sound wave, if we're talking about like human speech, that vibrating source is going to be the vocal cords in your throat. They're actually vibrating several thousands of times per second in order to create a frequency or a certain pitch. So the three types of waves that we usually encounter, like we see, you can create like water waves and see actual physical representation of waves, like a rippling effect. Like I said earlier, sound is probably the most common form of a mechanical wave that we interact with. We're always interacting with sound. We can always hear things. And then another great example is like a slinky. You can have like a slinky, and to demonstrate that for a wave. Um, Now, when we're talking about waves in terms of a medium, a mechanical wave is a type of wave that requires a medium. So the wave really depends on the medium, and the medium is the identity of the matter that the wave travels through. So we might not know this, but maybe you've played this game like in a swimming pool, where like you try to talk to a friend underneath the water. You can still hear sound underneath water, and it sounds different than it does in air, for instance. But let's say we're taking a look at this graph right here, and the graph says speed of sound in different media at 25 degrees Celsius, which is about room temperature. And you can see here that the speed of sound really depends on what type of material it's traveling through. If the speed of sound is traveling through air, if I'm talking through air right now, the speed of sound is 346 meters per second. Now that might seem fast, but if you think about it, think try to picture like 3.5 football fields. You can actually see that distance. You can see someone stationed away 3.5 football fields if they're just standing stationary at one end and you are at the other end. They might be really small, but you would still be able to see them. Now, if that person were to uh, clap their hands in a way that, or make some type of noise where you would be able to notice them making that noise, like visually see them, you would not be able to hear that until 1 second later, because the speed of the sound is traveling at 346 meters per second. And notice that the speed does increase as the state of matter changes. So there's a couple of things we want to infer from this graph right here. One is that the speed of sound changes depending on the state of matter. And to be more specific, It really depends on the medium density. So the more dense an object is, the faster the speed of sound is going to be. And you can see here from gas to liquid. Liquids are obviously more dense than gases, so the speed of sound is going to be a lot faster. And solids are far more denser than liquids, so you can see that the speed of sound is even faster there. The other thing I want to point out in this graph is that the title, so speed of sound in different media at 25 degrees Celsius. There's a specific reason why we included this term at 25 degrees Celsius. This is a measurement of temperature, so that means that the speed of sound must change at different temperatures. And we'll learn about that later, how the speed of sound is affected by the temperature of a medium. All right, so we're going to talk about the two main types of waves that we encounter. And the first one is going to be, well, first let's read this. The type of wave is affected by whether it needs to travel through a medium. So we discussed what a medium is. It's basically a substance that a wave travels through. If it does need a medium to travel through, that is going to be called a mechanical wave. And the mechanical wave requires a medium to travel through no matter what. An example would be like a sound wave. Sound is a great example of a mechanical wave. It does need a medium to travel through. So if you're listening to music or if you're talking to someone, you are interacting with sound traveling through air. Now, if you were to go into a vacuum chamber and take out all of the air, sound would no longer be produced. You cannot have sound if you do not have air. So if you're in outer space, you would not be able to hear anything. So the next time you watch like a Star Wars movie or Star Trek or anything that happens in outer space, basically, and there's a scene where there's like explosions or some type of battle, the most realistic way to experience that is if you mute your TV because, like I said, there is no sound in outer space because there's no medium for the sound to travel through. So I do have a really quick demo. We're going to watch this really quick.
Bell in vacuum. When sound waves travel in air, they vibrate the millions of microscopic molecules that make up air. In this experiment, a bell in a plastic container vibrates to make sound waves. Katie turns on the vacuum pump to remove the air from the plastic container. She pushes on the lid to seal the container. As the air is removed, the bell sounds quieter and quieter, even though the hammer on the bell continues to vibrate as hard as ever. Without air, the sound waves cannot travel from the bell to the walls of the container. Now, Katie turns off the vacuum pump and opens a valve. As air rushes back into the container, the sound of the bell becomes loud again.
All right, so that was just a representation of how sound requires a medium to travel through, making it a mechanical wave. All right, so the other type of wave that we talk about is going to be an electromagnetic wave. And an electromagnetic wave is a type of wave that does not need a medium to travel through. And you can see here that there's a picture called the electromagnetic spectrum. And this will be more covered later in Unit 8 when we talk about light. But the electromagnetic spectrum is a movement of energy without the necessity of a medium. So you can see here gamma rays, X-rays, ultraviolet rays, visible light, infrared, microwaves, and radio waves are all different types of electromagnetic waves that we can interact with. Some of these you've probably heard of. I know for a fact that you've definitely heard of ultraviolet rays in terms of like skin cancer and things like that. Infrared, you might have heard of that. Microwave waves are used for cooking foods and other communication devices, and then radio waves are used for other communication devices like radios, like FM, AM radios. The electromagnetic spectrum, if we were to break it down like this, you can see here that the waves are actually getting much, much shorter. And this is not a true representation of how long the waves are. If we are taking a look at the first section, which is radio waves, that includes AM radio, FM radio, TV, old TV stations could be broadcasted through radio waves, and then radar. One single wave, so when I'm talking about a wave, it's going from the top of one to the top of another. So that's one wave. If we're looking at one wave for an AM radio, the one wave is going to be 100 meters long, so almost as long as a football field, or actually longer than a football field. One FM radio wave is going to be 1 meter long, so it's going to be about 3 feet, just a little over 3 feet. And then if we take a look at the complete opposite side, you can see here that ultraviolet rays, X-rays, and gamma rays, they're on the nanometer scale, so that's very, very thin. You would not be able to see these with your naked eye. So these are going to be rays that are extremely small, very, very small waves. Now, if we take a look at this entire spectrum, only this tiny little sliver from here, from this red band over here, to this violet band over here, is visible light, and that makes up every single thing that we can see. And the visible spectrum is all the way from this red to this violet over here, and that kind of makes up all of the different frequencies. That doesn't mean that we cannot interact with infrared or ultraviolet. Like I mentioned before, most of us are aware that ultraviolet light does impact us negatively. It does impact us positively as well. We need ultraviolet light in order to produce vitamin D in our bodies, but it can also lead to serious things like skin cancer, for instance, which is one of the most leading causes of a preventable cancer. Ultraviolet light, of course, the major source of that is the sun. There are animals that can see ultraviolet light. I know caribou, for instance, can see ultraviolet, and I think there are studies that show that even cats and dogs can see ultraviolet light. There are animals that can see infrared light. I know snakes can see it, frogs can see it, and a lot of fish are able to see infrared light. X-rays are going to be used for, of course, taking an X-ray picture. That's going to be an energy source that travels through your skin and hits your bone, and then your bone is dense enough that it reflects that back. And that's how we can produce pictures of X-ray. And then gamma rays are very dangerous. We can find them in outer space mostly. And when we do radiation, that the unit in radiation, we'll talk more about gamma rays and how dangerous they can be. So we know that ultraviolet rays can give us cancer. X-rays, if we're exposed to them for long periods of time, can also give us cancer. And gamma rays are also very, very dangerous, and they can also give us cancer. So basically what we can infer from this is that the stronger the wavelength, the smaller the wavelength, the stronger the electromagnetic ray and the higher the chance of developing some type of cancer, or how dangerous it is. This is a picture of a remote control, and you can see that this remote control has a little light on it. Now, if you were to take a normal remote control that has a little bulb on the end, you would not be able to see a light shine from the remote control like this. By pressing a button, you're making the light shine here, and it's going to be flickering at a certain pace. The reason why you can see it in this is because the camera has the sensor in the camera has the ability to pick up infrared waves. So it can actually see those infrared waves and then process them as a picture. So the camera was able to take this remote control and actually see infrared. If you want to try this out with your phone, you can try to do this, but I believe most phones have an infrared filter, so you wouldn't be able to see a light coming from your remote control. But that's how remote control technology works. It has a little infrared button or a light bulb, and it blinks at certain intervals depending on what button is being pressed. So those were the two types of waves. The two types of waves that we covered were the mechanical and the electromagnetic waves. They can come in different shapes, and we're going to cover that next. So the first shape that we're going to talk about is a transverse wave. And a transverse wave is when the medium moves at right angles to the direction of the wave. So what I mean by that is that if we have a wave moving from left to right like this, the individual particles are going to be moving at right angles or perpendicularly to that wave. So remember, we said a wave was moving from left to right. That means the particles are going to be moving up and down and perpendicular to that. So I believe I have an animation that I want to show you right here that shows a transverse wave. And you can see here, we can follow one wave along like just kind of following that wave along with your finger or with your eye even. But if we take a look at individual particles, they're only moving up and down. They're not moving left and right with the wave. So even though the wave is moving left to right, only the particles are moving up and down. So this is very similar to like when I was talking about a wave in a crowd or something like that. You can see that a transverse wave moves up and down. The particles themselves move up and down as the wave moves left and right. So just remember it's at a right angle or perpendicular, and that's what defines a transverse wave. All right, let's go back to where we were. The next type of wave, so we covered this. The next type of wave was, actually let's cover this for a transverse wave. Transverse waves also have what's called a crest, which is the highest point right here. These are crests. And the bottom part, the lowest point, is called the trough. All right, so crests and the troughs. And one wavelength is a measurement from one crest to one crest. You could even do one trough to one trough. So like if we had a trough here, and then if this was a complete wave, you could do a trough over here. And then that would also be a wavelength. It is not the measurement of a crest to a trough. That is not a wavelength. You have to go from crest to crest. And that's how you measure the length of one wave. The next type of wave we're going to talk about is called a longitudinal wave. A longitudinal wave is when the medium moves back and forth in the same direction as the wave. It does not move perpendicularly or at right angles. It moves parallel to it, so it is going in the same direction. It is also called the compressional wave, and actually if we go to our little video here, or our animation here, you can actually see the wave is moving left and right, but the individual particles themselves are also moving left and right, but just kind of swaying back and forth like this, kind of just going left and right, back and forth in response to the wave. You can actually see there's a couple of terms here: compression and rarefaction. A compression is where you can see the wave is almost compressed, and the rarefaction is going to be the points in between the compression where it's kind of expanded out a little bit. So if you compress one point, you have to expand out another point. So you can see we have compressions and rarefactions. All right. Longitudinal waves, like I said, have compressions where the particles are together and rarefactions where the particles are spread apart. Like that, that's a compression, and that would be a rarefaction. The last type of wave that we're going to talk about is going to be a surface wave. And surface waves occur near the boundary of two different media. So these are going to happen when you have two different media occurring at the same time. The most common, or the best example that I can give is probably you have air as your first medium and water as your second one. So you can see that there's a difference of medium there. And surfaces move up and down, but also slightly back and forth. So not only do they move up and down with the wave, but they are moving left and right as well. So what does it look like when you're going up and down and left and right at the same time? Well, we could show you in this little animation here. Let's actually exit out. And right here. So this is what a surface wave would look like. You can see that this individual particle over here, this is going to represent water, this blue, and the white above it represents air. And the particle over here is moving up and down, and at the same time moving left and right. So you can see that it moves in a circle, and these are what surface waves look like. Notice the size of this circle and the size of this circle over here. So the further we go down in the medium, the smaller the circles we are going to get. So this is a great example of like what might happen in an ocean or a lake or a swimming pool, where you have two different media occurring, for instance, like water and air. So those are the three different shapes that we covered. We had, as a review, longitudinal, transverse, and surface waves as our shapes. And for the types of waves, we had an electromagnetic wave and a mechanical wave. So this concludes Notes 1 on the types and shapes of waves. Be sure to do the practice problems, and we'll talk again when we get to Notes 2, the characteristics of waves.